So today I'll talk about a cross-entropy method and a simple decentralized extension we have developed on that. And the majority of the talk is based on a paper that we published last year at Europe's. So it's not super timely, but I would say it's relevant today. And it's joint work with Jinjun, Martin, Luojun, and Dale. And so here's an outline of the talk. I'll first try to motivate why we even care about cross-entropy method, especially for an reinforcement learning audience. And then I'll explain what do I mean by decentralizing that and why do we want to do it. And after that, I'll show how we can use that for planning with a learned model and some benchmark results. In the end, I'll discuss the pros and cons that I've seen of this proposed method. Okay, so what is cross-entropy method? In short, it's CEM. It's a gradient-free optimization method. And it was developed first in the year of 1999, and then used in for policy search in RL. And so it's quite effective in dealing with non-convex optimization problems. In fact, you can find a lot of test functions online about non-convex optimizations. And I'm showing two of them here. And so it contains a lot of local optimum. And the global optimum is often quite hard to find. But if you run CEM, especially on those test functions, it performs extremely well. And because it's an optimization method, it can find applications in reinforcement learning. And so first, in model-free setting, it has been used to optimize the critic, this Q function, which is a learned function that encodes the value or the expected return you can get by taking action A in the state S and then follow some often optimal policy afterward. And so in model-based setting where we now have a model where we can do some like imagined rollout into the future using the model. And CEM has been used to optimize the return. So let's dive into the mechanism. So really, it's a simple mechanism that iterates between two main steps. So given some function that we try to maximize, we start from sampling. So it first would start from a parameterized sampling distribution G5 of X and sample from it. And from there, we select the top K samples in terms of the function values. And then we would update this sampling distribution by maximum likelihood estimation, MLE. And so there's this two steps. So why do we have the name cross-entropy there? And the reason is there's this equivalence that when we try to perform MLE on this top K samples, what we're equivalently doing is minimizing this cross-entropy between two distributions, P and G, and where this P of X is an approximated target distribution introduced by this top K samples. And this G of X is our current sampling distribution. So iteratively, on a high level, we want to move this sampling distribution toward better samples. And eventually, and that better sample would be the best samples in the solution space. And we can use this a picture to illustrate this process, where this big open circle represents some sampling distribution. And very often than not, it is a single Gaussian. And then we take those solid dots, which are the samples. And from there, select the top K, the blue samples there. And so what I forgot to explain, what does this square represent? It represents, you can think of it as a value landscape. So the more red it is, the higher the value it is. And on the left bottom, we have the global optimum, and there's a couple local optimum as well. So when we started this work, we're like, okay, it's quite effective in practice, and we would like to improve it. And since it's so simple, it's got to be really easy to improve. And it turns out it's not the case. And so let's first look at the literature to see what people have done. Maybe one obvious approach is just to increase the sample size. So yeah, it does increase the performance a bit, but it also increased the computation. And there was work that shows the performance would plateau before it even reached an upper bound. So another approach in the literature was this differentiable top K. And then after you do that, so top K is not differentiable. And if you make it differentiable, then gradient is your friend. You can do some magic, but the performance drops. And another approach is we can combine CEM, which is gradient free, with gradient ascent or descent. And what we saw is that there was no performance increase in Majorco control. And so there was also this approach that tries to make the sampling distribution more expressive, because I mentioned that very often people just use a single Gaussian, and a single Gaussian is unimodal, but we have this landscape which is multimodal, and it just doesn't seem to have the capacity to capture the multimodality. Now, one very naive extension is, now let's just throw more Gaussian at it. So this Gaussian mixture model, GMM, does that. But it's slow, and performance was not clear. By that, I really meant that, at least in the paper I'm showing here, the environments they used were not standard. Those were some modified environment only used in their paper and not in any other work. And we can take it one step further by just using a neural net. But it made the process a lot more complex. And it was only tested on toy problems. And even on those, you need other tricks to make it work. For example, beside the sampling distribution, you also need a second policy that does the sample to train, to collect data to train the neural net. And so beyond the toy example, is really not clear whether it's useful. Okay, so if we zoom out a bit, and just look at the timeline. So it started from 1999, and fast forward to 2022. So if we look at the best approach, so if I'm a beginner to CEM and I just want to maximize the performance, what variation should I use? And the answer is like most often the vanilla CEM that just runs the Gaussian distribution. And we mentioned that it has obvious limit, especially for dealing with non-convex optimization. And so we could increase the sample size to squeeze out some performance. if we are willing to pay the compute price. But we really like to understand whether we can improve CM performance without increasing the sample size. So by the way, the year cutoff was because that was the cutoff for the I guess the training data for this work. So with that, we're into the second part about this decentralized CEM. It's quite simple. We just take the big circle and break it down to smaller circles. It's really that. The smaller circle, the size represent the fewer samples. And we're running multiple CEM instances, and each runs independently with only a subset of the total sample budget. And it returns the argmax among all the instances. And one key difference is that in the centralized CEM, we do a global top K. So look at all the samples and select the top K. But in the decentralized version, we do a local top K. And just to explain the intuition a bit more. So we know that multi-model optimization can be difficult even in low dimensions. And maybe the best way here is just to be practical. Let's just do local search and plus random restart. And what each instance does is the local policy improvement. Then we aggregate the information by a simple argmax. Now, they are independently updated in contrast to some previous approach that does a coordinated update. And the benefit of updating them independently is such that they are less sensitive to local optimum during this top K reunification. We're gonna see that in action in some motivation example. We have this toy example just for verifying our intuition, and it's a one-dimensional optimization. It has a couple local optimum and one global optimum showing in red here. And it's a really simple problem because at just, let's say, take 100 samples and do a uniform grid search, we're gonna get really close to the global optimum. But let's see how CEM works in this setting. I'm showing the result on the right, and the way to interpret it is on the y-axis, we have the function evaluation of the solution of each method, and the lower the better. And this line here is where the global optimum is. And on the x-axis, we have the total sample size. And we're comparing three different methods. The first CEM that runs a single Gaussian, second CEM GMM that runs a Gaussian mixture model. And in the end, we have our DecentCEM method. And the line and the shaded region denote the mean and the max and mean over 10 rounds. And for each dot showing on the plot, we already did a hyperparameter search for each method and each population size. So it's showing the best that each method can achieve. And so the DecentCEM is the only method that could consistently find the global optimum, where CEM always got stuck in this local optimum. And even if you make it more powerful with GMM, the performance would vary. You would really need to increase the sample size to this 1,000 to reach a consistent solution on the global optimum. So we can take a closer look at the sampling process. On the left, we can see that we're taking samples and we're showing this density of this sampling distribution. And not surprisingly, the CEM with a single Gaussian got stuck because it only has one Gaussian distribution there. Somewhat surprisingly, even if you make it multiple Gaussian, it does not work. And the reason is, so let's look at the iteration 0. In the beginning, it did find some samples around the global optimum. But what happens after that is that when you take the top K, and because you have more samples toward the local optimum, it dominated the top K, and you have more samples there, and which attracts more distributions. As you iterate that, it makes sense whereas and cause this premature convergence. And those, like all the distributions you have all converge to the same point. And the decentralized version was the only one that can keep enough diversity of modes even toward the end. As you run more iterations, we have more results in the paper, and that shows later on in the iteration, it still was able to find more modes. Okay, convergence. Now, this part is more for the peace of mind. So CEM for continuous optimization, which is what we care about, has an almost sure convergence to local optimum. It was established in the literature in the year of 2011. And we try to make sure that when we decentralize it, we do not break this convergence result. And it turns out to be trivial. The reason is, in theory, they assume that the samples grows polynomially with iterations. And of course, when you use a constant number of instances, it's not going to break that. So each instance still converge. And this argmax would take the best result. So the end result would still be convergent to the local optimum. Okay, so that concludes this part about decentralized CEM, which is still in the optimization setting of a single function. All right, so then I'm going to talk about how we can take this decentralized CEM and use it for planning with a learned model. Since I haven't covered RL yet, I'm gonna just set the notations first. So we assume that we have this Markov decision process where the state action is denoted by S and A, and we also have this reward R. And there are many methods that you can use for planning. We are focused on this approach called model predictive control, MPC. Now, the idea is that we want to leverage a model, look into the future, and select the action sequence over a time window that maximizes the return and the imagined return. And so the model comes in here to do an imagined rollout of H steps into the future. And there's also value prediction, which is most often ignored in MPC literature. It's also ignored in our work. So we're almost entirely focused on the planning side of things, but just to get the model learning out of the way, what we use is an ensemble probabilistic neural net. And each network predicts the mean and diagonal variance of a Gaussian distribution, and is trained by minimizing the negative log likelihood. So all the methods that we're going to discuss in our experiments follow exactly the same model learning procedure, just to make it fair. And then we can just focus entirely on the planning aspect of this. Okay, so if I run the planning with a single CEM instance, it looks like this. So we start, so we run the CEM that starts from sampling distribution, and it samples from the model and gives back the optimal action sequence that it picks, and then we take the first action. Now, we need to find a way to initialize the sampling distribution. When naive approach is just set some initial parameter and use the same thing for all the states. And so one more advanced approach is where you add this policy net, and such that it learns for different states what are the best parameters you can use to initialize the CEM. And in the decentralized approach, we are making it parallel. So you can see there are different paths here, and each runs independently from each other. And one thing to note is the training process. Before we take this argmax, we run the training. So the data for training the policy net is collected before we aggregate the information for argmax, and that allows us to have different data for training the policy net. We're going to go over that benefit later on. I'm just going to pause here because I need some water. Okay. So for benchmark, we have looked into several environments, including gym, Mojuko, and some similar tasks. And we took a number of baselines that all use centralized CEM approach. And then what we do is we take those approach and change the CEM component to be decentralized while keeping all the other components fixed. That way we have a fair comparison. And there are two key methods that I need to briefly go through here. The first one is called PET. Essentially, you use that ensemble model and plus vanilla CEM for planning. And when we decentralize it, it's just called decent PETs. And next, we have the poplin, where they add a policy network to initialize the Gaussian. It works better, and it comes with two modes. The first one is the action mode, which is what we saw in this picture. Sorry, this picture right here. So it just gives back an action sequence, and you can do the same thing in the parameter space of the policy net as well, instead of the action. That mode is called poplin-P here. Okay. And for each variation, we have the corresponding decentralized version of it. We ran this on this benchmarks, and I'm just showing a few environments here. That's more representative of the result. You can find the full results in the paper. And what we observe is that in most environments, so first, the decentralized approach doesn't always outperform the centralized one across the board, but in most environments, they do perform better. And you can take some time to look at this figure more closely. we also added a model-free method, SAC, just as a comparison to show the sample efficiency difference. And so for ablations, we mainly try to answer 3 questions. First, does CEM work better with the same number of policy parameters as DecentCEM? Now, the catch is that when we decentralize and having that multiple path, we do have multiple copies of the policy net, essentially increasing the number of parameters, and that's not fair. We could make it fair by allowing CEM to use a bigger policy net, and we're going to see the result in a bit. And the second question we try to answer is that how does the performance vary with the number of CEM instances? And we also want to make sure that there's no mode collapse in the ensemble. All right, so we just need to pay attention to these 2 methods that have this bigger policy net suffix, and that's what we did to make the to increase the number of policy network parameters such that it's equivalent to that used in the DecentCEM version. Okay, and so after we make it fair, the performance drops, the performance of the centralized CEM approaches, and it became obvious in retrospect because I mentioned that how when we decentralize it, we use multiple data sources to train the net. And that's important because if you just blindly use run CEM with 1 policy net and just make it bigger, you don't have enough data to train it. As a result, you wouldn't expect to see a performance increase. In fact, that's what we saw here. If you look closely, the yellow line really underperforms the other method, and also this brown line also doesn't work so well. And so we can conclude that the decentralized formulation has more effective use of the policy net. And the second ablation is on the ensemble size. So we like to understand how we can best set the ensemble size. And so what we did is we take the richer environment and increase the ensemble size and check the performance. And the observation is that, like in some case, having a larger ensemble size is better, like in the DecentCEM-A version. But in some other case, after you reach some point, it starts to have diminishing returns and even worse performance. Like this one, if you have 6 CEM instance, it's performing worse than the green line, which is just using 3 instances. So there is a trade-off in the ensemble size. As ensemble size goes up, we're really trading off accuracy of the sample mean for better exploration by more instances. And so unfortunately, to this point, we still don't really know how to systematically set the ensemble size. But one thing we do observe is that in majority of the environments we tested, it is better to have at least more than 1 instance. So that's reassuring for taking this ensemble approach. In the end, we want to check when we run multiple instances whether they collapse. Right? So for that, I took the simplest environment, the pendulum in this benchmark. And so on the left, I looked at the selection ratio, which is essentially how often each instance gets used in this argmax. And so they don't. So each instance, as we see here, has some chance of being selected. And if we look into the action statistics showing the center here, the line is the mean and the shaded region is the, I think, the mean and max. So it's so the full training is 10,000 steps. So I'm really showing like toward the end of it, even at that timestamp, there's still enough diversity there. And more closely, we can look at the pairwise distance of actions. And it's still not going down to 0. So we can say that there is no mode collapse, even in simple environments where you might expect, because it's too simple that the mode would collapse into the same solution, but it's not the case. So, so this brings me to the conclusion of it. So what are the pros and cons of DecentCEM approach? So the pros, first, is simple to implement. And we just need to run the same procedure and just add a layer on top. And it's an effective way, as we show in the benchmark results, that we can improve the CEM performance at the same sample size. So for the cons, as I mentioned, there's a lack of systematic ways to set the ensemble size. So yes, using ensemble is good, but we don't really know how to find the sweet spot of the ensemble size. On the implementation side, it's running legacy TensorFlow 1 code, so it's really hard to manage. And currently, the implementation is 0, rather than it can be parallelized. Right? So each instance should be running in parallel and only in sync at the argmax step. So there's some room for like better and faster implementation. So the last 2 points here, I think, can be addressed simultaneously. And so yeah, the paper and code is here. Thank you for your attention.